Speaking of where functions exist and or are defined, brings us to the topic of is this pen really good? The topic of domain and range, but domain is about where functions are defined. So I know I've spoken about domain, I've mentioned domain here and there, everywhere, but let's really get down to business and kind of define it super precisely. So domain, very kind of broadly is, and this is class R. Class R. So domain is all possible values of x that can be plugged into a function. And there's one kind of qualifier that I'll mention in a minute, but we'll talk about this first. So we can usually look at the domain, or we can usually find the domain by just looking at the graph or by looking at it algebraically. I'm usually more of an algebraic, so you can kind of see the domain graphically, but it's usually easiest to do this way. So algebraically, sure, that's close enough to have that spelled. We can find the domain as follows. So here's how we do it. So what we say is the domain is all real numbers. The domain of a function is all real numbers, which we often write as the set of numbers from negative infinity to infinity. So unless one of the following three things happens. So unless you either have division by 0, so if there's some way that you might divide by 0, we're going to, let me use this in red here. Sorry, I know I have a decent red pen somewhere. Yeah. We're going to set the denominator equal to 0 and exclude those values. Or if we have a square root of a negative, so if we have a negative, I say square root, but really it's any even root. So if there's a 4th root or a 6th root or an 8th root or a 1000th root, we have a negative in an even root, like the square root of something, the square root of some stuff, or the 4th root of some stuff. If that's the case, then we're going to set the inside of the root to be greater than or equal to 0. So we're going to set, I guess I'll call it stuff since I've already called it stuff. We're going to set the stuff to be greater than or equal to 0 and then solve that inequality, which can be somewhat challenging. The last possible domain issue we might have is we have a 0 or a negative in a logarithm. So something that would give 0 or negative in a logarithm. Again, all this is spelled out in the class notes. You should definitely look at them if you want to. So we're going to, in this case, if you had the log of something, right, we would set, I suppose if we had, right, like log of some stuff log base 10, log base 2, natural log, doesn't matter what the base is, as long as it's allowed. We would be setting the stuff to be strictly greater than 0. So those are the three things we look for when we're asked about domain. Is there division by 0? If there is, we want to not include those points. Is there an even root? Okay, we want the insides to be non-negative, greater than or equal to 0. Or is there a logarithm? Okay, then we want the insides to be greater than 0, positive. Those are the three kinds of things. And then as far as range goes, for now, we will just talk about range in the context of looking at the graph. But I know last class we talked about inverse functions, and the next class we'll kind of talk more about how, in fact, I know I talked about last time how the domain of the inverse is the range of the original and vice versa. We'll definitely use that in the next class to find the ranges and functions. So for now, I'll just say, so the domain is all possible values of x that can be plugged into a function. The range is all possible y values that we can get at. And I guess I should write that down. So the range of a function is all possible y values. I should say all possible y values that result from the domain. And there are two ways to see these. We can either do it graphically, which is what we'll talk about somewhat today, or you can find it by finding the domain of the inverse function. That only works if the function actually is invertible. So domain is usually, or sorry, range is often a little more challenging than the domain. So let's look at an example. Let's say we have, I want to find the domain and range of the following function of f of x equal to x squared minus 2x minus 15. Okay. Domain. Is there division by 0? Nope, there's no fraction. Is there a square root or an even root? Nope. Is there a logarithm? Nope. We're good. We don't have any of the three problem functions, so the domain is everything. So you can either write the domain as, it's fine to say, you can say all real numbers if you want to write all those words. You could, my preferred way of doing it is writing it as the set containing negative infinity to infinity, or really everything in between. If you really want to, if it happens to be everything, you can also use this fancy R, which just is two vertical lines and then with an R. So those are three different ways of saying all real numbers. The range is not. This graph is a parabola. We know that for a parabola, the range is limited by where the vertex is. So it's always weird looking at myself and like my eyes are totally cut off. I'm like, here's my mouth just talking, no eyes. Okay, there's my eyes, but I'm not that sure. Right, my computer doesn't tilt up anymore, so you're just gonna get sometimes just here below. Oh. So to find the range, let's do a little bit of graphing. You don't actually have to graph the thing, but we're gonna graph it. So let's find the vertex. The vertex, let's see, the x coordinate is negative b over 2a, which is, let's see, negative 2 over 2 times 1, which is 2 over 2, which is 1. And then the y coordinate of the vertex, we would plug in the 1 to the function. It's going to be f of 1, which is 1 squared minus 2 times 1 minus 15. 1 minus 2 minus 15 is negative 1 minus 15 is negative 16. And if you know which way the parabola opens, you know enough information. You say, okay, this parabola opens upwards. So this negative 16 is the lowest y value. So you could, without drawing it, say, hey, the range, I'm going to write it this way first. Y is going to be bigger than or equal to negative 16, less than infinity. The actual way I want you to write the range, if it's like this, is using the interval notation, which is going to be bracket negative 16 to mean that negative 16 is included all the way up to infinity with the parentheses because we never include infinity because it's not a real number. If I was drawing this, the vertex would be positive 1, negative 16, so like maybe somewhere over here. And then it would open upwards. Right, there'd be a y-intercept of 0, negative 15. This probably factors, and you have like an x-intercept of negative 3 and x-intercept of positive 5. But you don't need any of that stuff if you're just trying to find the range. You say, okay, well, the lowest y value is negative 16, and then I get every y value that's above that. Okay, something else to mention here. This is not super important for this class, but this does come up occasionally. So when we're talking about domain here, what we're actually talking about is what's called implicit domain. Meaning if I just tell you a function and say nothing else about it, we're like, oh, the domain is just whatever x is allowed to be. But sometimes people actually specify a domain. So, because sometimes the function is supposed to like represent a thing. So let me give you a different example and we'll talk about kind of how it makes sense. Because this does come up a lot, especially, I would say mostly in the 17 series, but also in the 16 series. So let's say we had, in fact, let's do an optimization problem. Yeah. So take it back a step. So I'm going to switch gears for just a minute. Let's do an optimization problem. So let's say, yeah, sure. So I want to maximize the area of the rectangle inscribed. I know this, we've done problems like this before. Inscribed under the line y equal to, I'm going to make it not super hard, y equal to, I want to make it kind of interesting though. Let's do 8 minus 2x. Is that going to be kind of interesting? Sure, yeah, why not? Sorry, one sec. In the first quadrant. Okay, so draw a picture. Y equals 8 minus 2x has a y-intercept of 8, an x-intercept of positive 4. No, we're not finding the domain of this function, although the domain of this would be everything, right? And here's my rectangle. With a base of x and a height of y. This is the point x comma y. But we know that y is equal to 8 minus 2x. So let's write an equation for the area. The area is x times y. Right? So base times the height. But then we know the constraint is y equals 8 minus 2x. So area is really x times 8 minus 2x. So I can say that area as a function of x, if I distribute this out, is 8x minus 2x squared. Okay, I guess we should finish the problem, then we'll talk about domain. So to finish the problem, we're going to find the vertex to see what maximizes it. So the vertex is going to be negative b. So the b value is 8, right, because I wrote this out of order. So it's negative b over 2 times my a value is negative 2. Negative 8 over negative 4 is positive 2. And then the y coordinate, not the vertex, right? If I find the vertex, that's going to give me the area. I don't want that if I'm trying to find the dimensions. I didn't write dimensions, but we usually find dimensions. So right, I'm not doing this. I'm just saying, oh yeah, this. Y is going to be 8 minus 2 times 2, which is going to be 4. So the dimensions that maximize this are x equal to 2, y equal to 4. Okay, here's the important question, or the question that sometimes comes up in future kind of classes. If you look at this function, what's the domain of this function? Well, do we have any problem functions? You guys are supposed to say No. Right, there are no problem functions here. There's no square roots, there's no logarithms, there's no fractions. So what I would say about this function is the implicit domain. And again, these are not words I use very often, but they are words that occur in other textbooks. If I'm saying domain, I mean implicit domain, meaning that if you just look at it, what should we exclude? Oh, nothing, right? The implicit domain here is everything. However, if we're thinking about this in the context of the problem, where we're talking about the area of the rectangle in the first quadrant. Oh, we're in the first quadrant. If we're in the first quadrant, that means x has to be positive. So our explicit domain that someone is telling us has to be true because of the nature of the problem. They're saying, well, first of all, we're in the first quadrant, so x has to be positive. So x has, I should say, x I guess could be 0, but it's a little weird. But fine, we'll say x can be 0. And also, since we're inscribed under this triangle, x can only go up to 4. So the explicit domain for this problem, the domain that makes the problem make sense in some way, is that x is between 0 and 4. Even though if you look at this function, right, clearly x can be anything, right? X can be 5, and if you plug in 5, you get 40 minus 2 times 25, you get 40 minus 50, which is negative 10. Perfectly fine for a parabola to have a y value of negative 10. But it's not sensible for this function, which represents area, to be negative. So again, context matters here, right? Implicit domain, free of context, we're just looking at the function saying what can x be. Explicit domain, someone has told you you are limited to this domain specifically. It's like in a piecewise function where I give you the different pieces and give you the explicit domain for each of those pieces. So that's what the explicit domain is. We don't really deal with it much in this class, but I wanted to make it clear that sometimes someone's going to give you a function and then they're going to tell you the domain is limited to something that it wouldn't normally be limited to. Whereas if someone just says, what's the domain of this, and they haven't said anything else, they mean implicit, look at the function and tell me what's missing or not. I know that someone wrote something down there. The range would be less than or equal to 6. Well, so it depends. Are we talking about? So we're talking about the range of this function here.
Like the area under the triangle. I don't know.
Sure. Well, yeah. So I mean, it's like, so if we're talking about, right, yeah, if we're talking about this function here, then the range is also limited, right? Because so clearly the smallest, well, maybe not clearly, maybe clearly, the smallest the area can be is 0. Right? If you had a rectangle whose base was 4 and whose height was 0, or whose base was 0 and whose height was 8. So the area, or I should say the range, the explicit range, right? If we are limited to this explicit domain from 0 to 4, is it's going to happen to also be 0 to 4 because the maximum area was 4. So it's not, it's just a coincidence they happen to be the same. If I change this number 8 to something else, just to make it clear, actually that won't make it clear at all because they'll still be the same. Yeah, sorry. It's maybe not super coincidental, but they're not always the same. So right, so here, right, the most the area could be is 4, the least the area could be is 0. Even though this function actually has a range of negative infinity to positive 4. Because this parabola, if you graph it, goes all the way down to negative infinity, but only as high as y equals 4. So actually, let me graph this for you guys just so you can see. So that parabola, a of x equal to 8x minus 2x squared, has x-intercepts at 0 and 4, and has a vertex at 2, 4. So it looks like this. So again, let me just say the things. So the regular domain would be everything. The regular range would be everything from negative infinity up to positive 4. Bracket on the 4. Cool. Wow. Okay. Come on. So that's regular domain and range, also called implicit domain and range. However, if we limit it to what makes sense, if you're thinking about this actually being the area depending on what x is, well, the area can only be positive. So we're really just kind of stuck with this part right here, where the explicit domain is 0 to 4, because x can be as small as 0 as big as 4, and the explicit range is this happens to be the same. Right? Y values go as low as 0, as high as 4. Don't get too hung up on this. We're not going to really talk more about this in this class, but I felt like I should at least talk about it once to kind of prepare you for it. In some classes, they will kind of say, oh, like this function, we only want to consider x values between here and here because that's the only thing that will make sense. Okay. Kind of funky though. Let's look at some more regular examples. So whenever I say domain, I will always mean the implicit domain, meaning look at the function and everything that x is allowed to be, that's our domain, meaning we're only going to exclude where you might have a division by 0, or you might have a square root of a negative, or you might have a logarithm of a 0 or a negative. So let's look at this next one. Let's find the domain and range of f of x equal to, what have I got here? The natural log of x plus 1 plus 2. So domain. We're also going to graph this one, but let's talk about domain. So for domain, we know for a logarithm, the argument or the inside, so that's x plus 1. It's all in fact right on the screen. Let me fix it. So the argument of a logarithm, whether it's base e or base 10 or base a million, the insides have to be strictly positive, which means x has to be greater than negative 1, which means on the number line, if negative 1 is right there, we are everything to the right because we are bigger than, but not equal to, negative 1. So my domain here is negative 1 exclusive, right? We use a parentheses if we don't want to include the point, but we want everything up to that point, all the way to infinity, exclusive. To find the range, we probably should just graph it. I'm going to take the natural log function. I'm going to shift it 1 to the left. My vertical asymptote is going to be x equal to negative 1. So it would look like this. That's just shifted 1 to the left. And then we shift it up 2. So fine, I'll just erase it and draw it again. So shifting it up 2 means instead of getting the point 0, 0, right, because I had 1, 0, and then shifted it left to 0, 0, and then shifted it up to 0, 2. Here's the thing about the logarithmic graphs in general. Their range is always everything. They definitely kind of peter out. Well, I should say they definitely taper off, right? They start to kind of, they look like they're kind of flattening, but they don't actually ever flatten completely. They still always are increasing, increasing, increasing forever and ever and ever and ever. It just looks like super slow. If you graph these on Desmos, if you graph natural log of x, it's going to look like a horizontal line, but it's not. It's just very slowly creeping up. If you zoomed out like a bajillion times, you would maybe eventually see that you can get to like 5. But like really, it takes forever for the natural log graph to even get as high as y equals 5. Because to, like, for example, if you're doing y equals a natural log of x, and you want y to equal 5, that means x equals e to the 5th power, which is, I guess it's not super huge. It's less, it's around like 200, but still, right? Like, I mean, it takes a long time just to even get to a y equals 5. But the range is everything. And that's true for any logarithmic function. The range is always everything. Unless you've artificially cut it off. Okay. Let's look at some more examples, some more graphical examples. Hope you all had a decent extra long weekend. It's the last extra long weekend until the end of the quarter. We got 4 weeks and then finals to go. We can do it. Also, actually, I should double check one thing. I don't think we have a test this week. I think we have a test next week. Let me double check that while I'm thinking of it. Let's see. Midterm 2 is February 28th. Yeah, so not the end of this week, which is the 21st, but the end of next week, which is the 28th. So I'll try and get some practice materials up sometime before the end of this week. Okay. And that's not what I was looking at. Yeah, okay, good. So the range and domain, or domain and range of f of x equal to e to the x. All right, e to the x has none of the problems that we're looking for. There's no fraction, there's no roots, there's no logarithms. So the domain is everything. Range, easiest to see by graphing. Or you could find the domain of the inverse function, but we're going to graph it. So here's the graph of e to the x. It looks like this. It's the usual kind of shape with a y-intercept at 0, 1. And we know that we have a horizontal asymptote at y equals 0. And not that you can't cross a horizontal asymptote, but this function does not cross its horizontal asymptote, right? The function is always above the x-axis. It never quite ever equals 0. So e to the x is always greater than 0. So here we know that y is always strictly greater than 0, which means our range is everything from 0 not inclusive or exclusive to infinity. That's it. Stop me if you have questions. Talk forever. Or for 20 minutes, you know, since we are limited by how long the class actually is. Okay, where'd you go, green pen? I have a whole other series of games. I try not to use up one pen all at once. I feel like if I space them out, they usually last a little longer. Let's look at one more graphical one before we start kind of focusing just on the algebra side of things. So let's say my function is, find the domain and range of. It's funny that I abbreviate domain, like I don't want to write those last 3 letters, but range I don't like. It's like, yeah. Range is 5 letters, I can write all those. Domain 6, too many. So domain and range of f of x equal to the square root of x plus 9. We can totally graph that. It's just the usual square root function, shifted 9 to the left. So over here, negative 9, right? So usually we would start at 0, 0. We're shifting 9 to the left. It's going to look like this. Not that we care, not that it matters or we care. We do care. The y-intercept is 0, 3. So here it looks like the domain, well, we're starting at x equal to negative 9. We get everything to the right. So the domain is negative 9 inclusive, right? We get that point. That is a point on the graph all the way to infinity. Or you could have actually done the algebra and said, look, x plus 9, the stuff inside the square root, has to be non-negative, greater than or equal to 0. So that x is greater than or equal to negative 9, which is exactly that, greater than or equal to negative 9. The range, it looks like the y values go as low as 0. Do we actually get 0? Yeah, we actually get 0, because if x is negative 9, y is going to be 0. So the range, just looking at the graph, is everything from 0 to infinity, with no negative values. Infinity isn't surrounded by, correct. Infinity never, ever, ever gets a square bracket. Infinity is always a parentheses, because a bracket means we include that number. But infinity isn't a number to include. It's just saying things just get bigger and bigger and bigger and bigger and bigger. Okay. So let's actually look at some more, what I think was more realistic examples where, yes, you can graph things, but not everything is easy to graph. And sometimes even if you can graph it, it's hard to really tell what the domain or range might actually be. Usually more the range than the domain. Well, let's look at, so these examples where we're doing the domain algebraically, we're not going to talk about the range for the moment. So let's look at this following one. I want to find the domain of f of x equal to x plus 2 divided by x squared minus 49. So again, I'm always looking for the three problem functions: logarithms, roots, and division by zero. Meaning, do I have a fraction? I have a fraction. I don't have any of the other things, all right? I don't have a logarithm, I don't have a root, an even root, I should really say. I do have a fraction. So for this one, I'm going to say I want to exclude where the denominator is equal to 0. So there's going to be 2 points I want to exclude. I want to exclude because, so I would personally factor, this as x minus 7 times x plus 7. And see that I'm going to exclude where x is equal to 7 and where x is equal to negative 7. You don't have to, but if you like, you can draw this on the number line to help you see what you have. So if you're just excluding places, I just don't want those numbers. So I don't want 7 and I don't want negative 7. But that's it. Those are the only points I'm picking out. I want literally everything else. I want everything from negative infinity to negative 7. I want everything from negative 7 to 7. I want everything from 7 to infinity. I just don't want negative 7. I just don't want 7. So the way I write the domain here, say, okay, I want everything from all the way down to negative infinity up to negative 7. Exclusive. I do not want to include negative 7, so it gets parentheses. Union, all of this. Everything from negative 7 to 7. Exclusive. Again, I don't want to include those points, but I do want everything in between. So this gives me like, negative 6.9999999. This gives me negative 6, negative 5, negative 4.5, negative 4, up to negative 3, negative 2, right? And all the numbers in between, not just the integers, right? Everything in between. And this gives me, and then also everything from 7 to infinity. So basically, if you're just excluding points, however many points you exclude, you're going to have one more than that separate number of intervals. So I excluded 2 points, and I broke it up into 1, 2, 3 separate intervals that I have to include. Let me give you another example that's not on my. How much time do I have before I start throwing extra examples in? Oh no, I'm good. No, the 7s have to have parentheses because we do not want them. Right? So if you don't want anything, it gets a parentheses. And we don't want 7 because if you plug in 7, you get division by 0. Let's look at another example that's not on the list here. Let's say we had, let's say I had f of x equal to the cube root of x plus 1 divided by x squared minus 4. Okay, so I definitely have division by 0 problems, and I don't have any other problems. I don't have any logarithm problems, and I don't have any even root problems. Cube root is perfectly fine. You can take the third root of a positive number, you can take the third root of a negative number. Right? The cube root of negative 8 is negative 2, because negative 2 times negative 2 times negative 2 is negative 8. So if you see odd roots, ignore them. They don't matter. They don't affect the domain at all. But division by 0 here is still a real problem. So we need to exclude where x squared minus 4 equals 0. You can factor x plus 2 times x minus 2. So we don't want negative 2. We don't want positive 2. So it's going to look very much the same as this. I really was just doing this one to point out that a cube root or any odd root is not problematic. So odd roots, ignore them. I want all of this. I don't want negative 2. I want all of this. I don't want positive 2. I want all of this. So I want everything from negative infinity to negative 2 parentheses, union negative 2 to 2 with parentheses, union parentheses 2 to infinity parentheses. Okay, I think I got 3 more examples. I'm pretty sure we can get those all taken care of. look at this next one, which has. No, that's fine. We can do that in the next one. Let's look at f of x equal to, what have I got here? 3x plus 5 over the square root of x plus 8. So here I happen to have a fraction and an even root. So there are two things I have to consider. Thing one, I want to exclude where the denominator is equal to 0. So I want to exclude where the entire denominator is equal to 0. You can do whatever work you want to solve this. You can square both sides and then subtract 8, or you can just see that if x is negative 8, then negative 8 plus 8 is 0, and the square root of 0 is 0. So, or you can square both sides, right? Square both sides, you get x plus 8 equal to 0 squared is 0 times 0, which is 0, and then x equal to negative 8. So we want to exclude that. And then we also need for the insides of the square root to be non-negative, greater than or equal to 0. So we want x to be greater than or equal to negative 8. Which means we want everything to the right of negative 8. So here's what we get. And again, you don't have to, but I like to draw the number line. Don't put a 0 on your number line unless it's one of the important points that's kind of coming up in this process. I'm only putting negative because it's the only point that really matters. Let's see. I want everything bigger than or equal to negative 8. But then I also said exclude negative 8. So that one there that I drew a circle or a point filled in, I really should open it up and say, I don't actually want negative 8. So I have to kind of, I'm really kind of making it look terrible. Because I have to obey all the things that happen. So I don't want negative 8 because this says you don't want negative 8. Because it would give me division by 0. So here my domain is everything bigger than but not equal to negative 8. I want negative 8 exclusive all the way up to all things. I should say negative 8 exclusive and then everything bigger than that. You say all the way to infinity. Kind of, I'm not trying to say you can get to infinity. I'm just trying to say you keep getting bigger and bigger.
James, I have a quick.
Go ahead.
I know you kind of explained it, but can you go a little more into detail as to why it's not a closed circle? Like why it can't be equal to negative 8?
So what happens if we plug in negative 8? Plug in negative 8. We're going to get 3 times negative 8 plus 5 over the square root of negative 8 plus 8. So that's going to be negative 24 plus 5 divided by the square root of 0, which is negative 19 divided by the square root of 0 is 0. But division by 0, can't do it.
Okay. Thank you.
No, you're welcome. That's a good question. Can't divide by 0. So that's why we have to exclude negative 8, because it would lead to division by 0. Something else that's worth noting here. You never want to simplify before you find the domain. Yeah, we probably haven't. Let's see. So just as an example, if someone gave you this function, if I said f of x equal to, sure, x squared minus 9 over x minus 3, yeah, you can simplify that eventually, right? This simplifies as x minus 3 times x plus 3 over x minus 3. And you can cancel the x minus 3's. But if you look at the original, which is what you have to look at when you talk about domain, x still can't be 3. So our domain is everything except for 3. Which is why this graph looks like the line y equals x plus 3, except there's a hole when x is equal to 3, because the function is not allowed to be 3, because if you plug in 3, you get division by 0. Yeah, it's 0 divided by 0, but that's still division by 0, which is still undefined. So good rule of thumb, if you're finding domain, don't simplify the function at all. Leave it alone, deal with it in its original form. Okay, 2 more. I think we can fit this one on this side, yeah. Let's look at this function. of x equal to, what do we got here? The square root of 2x plus 5. I think it's a minus in the notes, so I changed it to a plus. Square root of 2x plus 5 divided by x squared plus 7x plus 10. And again, there are two things to consider here. Thing one, I don't want division by 0. So we need to exclude where x squared plus 7x plus 10 equals 0. This factors is x plus 5 times x plus 2. So I want to exclude x equal to negative 5 and x equal to negative 2. So already on my number line, I know I don't want negative 5 and I don't want negative 2. I'm not going to draw anything in yet because this square root might tell me other things I have to do. So then for the square root of 2x plus 5, the inside, right? I don't write the square root of 2x plus 5 is greater than or equal to 0. I write the 2x plus 5. The argument of the even root has to be greater than or equal to 0. So subtract 5 from both sides. 2x is greater than or equal to negative 5. And then divide both sides by 2. X is greater than or equal to negative 5 halves, which as a decimal is negative 2.5. So that's going to be maybe right about here. There's negative 2.5. And this says I want x to be greater than or equal to negative 2.5. So I'm going to include that point because it's greater than or equal to, but then I only want everything to the right because it's greater than. So I want everything to the right. Oh, I don't want negative 2 though, because we said we had to exclude it. I want everything over there. I don't want anything over there. So yeah, negative 5 is excluded, but it's also just not working here because if you plug in negative 5, you get the square root of the negative, which is not okay. So here our domain would be negative 2.5 bracket up to negative 2. We have to exclude the negative 2. Union negative 2 to infinity. And I really should try to squeeze in one last example here because it is important to do this last one. I know it's 11:48. I'm going to do it. The last example is the following. Find the domain of the natural log of x to the fourth plus 9x cubed plus 14x squared. So here we have to say, well, we need the inside or the argument of the logarithm to be strictly greater than 0. And the only way we can do this if it's a non-linear thing, meaning you have powers of x that are different than 1, is by factoring. I can factor out an x squared, look at the x squared plus 9x plus 14. And then I can factor this even further as x plus 7 times x plus 2. Because 2 times 7 is 14 and 2 plus 7 is 9. So here's what we're going to do. We're going to look at the places that make this equal to 0. So I get x equal to 0 with a multiplicity of 2. I get x equal to negative 7 with a multiplicity of 1. And I get x equal to negative 2 with a multiplicity of 1. So I've got negative 7, negative 2, and 0. Do make sure things are in the right order. If they're not, things will go crazy. So what you could do if you wanted to is you can kind of think of this as a polynomial for a second. I mean, it is a polynomial if you ignore the log. It's got an even degree. It's got a positive leading coefficient. So the end behavior is up on the left and up on the right, which means all the way to the left, it should be above the x-axis, so it should be positive. All the way to the right, it should be above the x-axis, so it should be positive. You could also just pick a number, right? You could pick something like 1 and plug it in and see that it's a positive times a positive times a positive. But now, at 0, well, 0 has an even multiplicity, which means it's going to bounce, which means if it was positive over here, it's going to bounce off and stay positive. And then -2 came from this factor, which has an odd multiplicity. So it's going to go from being above where it's positive to crossing through and being below where it's negative. And then -7 comes from this factor, which also has an odd, so it's going to cross from negative to positive. So really what I'm actually thinking of is graphically, it looks like this. I'm positive. I bounce off at 0. I go through at -2. I go through at -7. And I want the parts where it's greater than 0. So I want all of this, not that. None of this, not that, but all of this. Oh, not that. And all of this. Oops. So I want my domain to be all of this. So everything from -infinity to -7 exclusive. None of that. But then I want everything from -2 to 0. But I don't actually want 0, so I have to break it up and say, okay, stop there, and then everything from 0 to 2. So I'm kind of using my knowledge about polynomials to help me figure out where this thing is positive or negative. So I'm saying it's positive over here, and then if it's an even multiplicity, it's going to stay the same, or if it's going to bounce. If it's odd multiplicity, it's going to change because it's going to cross.